is parametric equations of lines. By the end of today, you should be able to write equations of lines in 2 or 3 dimensions parametrically, symmetrically, also write the vector equations for those lines, and finally, if there's an intersection of lines, be able to determine what that intersection point is.
What is parametric?
That's what we're going to define right now. So, suppose a line L in 3 dimensions goes through a point P naught with coordinates x naught, y naught, z naught, and is parallel to a non-zero vector, v, we'll call it. And let's just say that this vector has components a, b, and c. Hey, Devin, we just started, so you didn't really miss too much. Then the line, and actually let me draw the picture first. So let's say here's a line. Let's call this point x naught, y naught, z naught. And there is a vector v that is either on the line, because that would be parallel, or just somewhere else. You know, maybe v is out here somewhere. So it's either on the line or just what we would normally think of parallel. Okay, but by default, if the vector is on the line, then that vector will be parallel to it as well. Okay. Now, in general, then L will consist of all points P, just regular old x, y, z coordinates, such that, so here's a point P now. And this was P naught. The vector from P0 to P is parallel to V. And I think in this picture that's clear, right? Any point on this blue line, if I connect from P to P naught, or vice versa, P naught to P, will be another vector that is parallel to the line. Okay? Now, with that being said, we have some implications. Okay, this implies, here's my black one, that P is on L if and only if, that's the abbreviation for if and only if, P0P. And now, this is where we need to just recall, how do I know if vectors are parallel to one another? That's if they're orthogonal. Not nope.
It's the unit vectors are equal,
That would be one. Yeah, that would actually work, but there's a much simpler way, right? Just look at it on paper, perhaps.
Cross product is 0.
Cross product is 0. That would work. Yes, there's a simpler way. The very way back, I think we talked about this. Here's tiny little vector. Here's another one that is parallel to it. What's the relationship? Oh, you guys can't see.
Two of the coordinates are the same.
Perhaps. Has to do with scalars.
You can divide one by the other and get a whole number.
Now we're on to something. I think, so you're talking about a scalar multiple, right? One is a scalar multiple of the other. That's all. That's all we need for it to have parallel. So if P0P is going to equal T times V. Okay, so we're calling T the scalar. This is just a scalar now. Okay. And if we go back to our definitions, let's write things out in component form. If I'm looking at the vector from P0 to P, from P0 to P, I would do x minus x naught to find the x component, y minus y naught for the y, and similarly z minus z naught. And then that's going to equal, on this side we have t times v. Remember, v is just ABC, so we can distribute the t to all three components. And now we have TA, TB, TC. And if these vectors are truly equal to each other, you can go component by component, right? This x component has to equal that x component, and so on and so forth. So we can now say that x, so this is the definition for parametric. So I'm kind of skipping a step, but hopefully you don't get too lost here. If I set this equal to the other side, I'm just going to move x naught over, and I'll have AT. Let's do the same with the y's and the z's. And this is your parametric definition for lines. Okay? When they're written in this format, we get a specific coordinate just for x, just for y, just for z, depending on the t parameter. Okay? So make sure you remember these, and we'll use them here in a moment. Obviously, it's similar in 2 dimensions. If I don't have a third dimension, then we just have this. We just remove the z component. That's all. Now, symmetric form. Yes?
What's the x minus x over? What's that? Like the x in that equation?
This is the x coordinates. Remember, I'm going from P0 to P.
Yeah.
So P0 is this. P, we do terminal minus initial to find the vector components. Does that make sense? Okay. Symmetric equations would then be, if you imagine solving for t, if you solve for t, you get t equals x minus x naught over a, y minus y naught over b, and z minus z naught over c. Thank you. You guys see how I'm getting that, right? Okay. Well, the symmetric format is just these. Since all three of these equal to t, we can now just set these equal to each other. So symmetric is officially x minus x naught over a, x minus, y minus y naught over b, and z minus z naught over c.
What is A again? And B and C.
A, B, and C are the three components to that vector that is parallel to or on the line. If you remember when you first learned point-slope form back in Algebra 1, right? When you were writing an equation of lines, you needed a point and a slope, right? This is very much analogous to that because we're going to have a point usually given to us, and we're going to have not necessarily a slope, although it's related to it. We're going to have what I call a reference vector, which is kind of like the slope. If you know that vector and you have a point, you can always find the equation of the lines. Okay. In fact, let's do an example. Find the parametric equations for the line through, we'll just go easy, 1, negative 2, 4, and parallel to vectors, vector v, which is 2, 4, negative 4. Should take you 15 seconds.
Right now we have P initial. So how do we find out P?
Don't need it. What do we need to write the equation of a line parametrically? We need a point on the line and a vector that's parallel to it or on it. Okay, let's see if we thought about this correctly. I mean, this is about as straightforward as it's going to get. You're given the point, so x naught is 1, and we go plus x component times t. And then same thing with the y's. Negative 2 plus 4t, and then 4 minus 4t. So this would be the parametric set of equations for the line. Okay. Now, just also be comfortable with different notation. Like you might see it written like this. I don't know, I wrote this down, so there must be a reason. Maybe on WebAssign they have it written this way where you're finding the equations, but you're writing it as an ordered triple. And so that would be the same thing. You just go, okay, 1 plus 2t, comma, negative 2 plus 4t, 4 minus 4t. Because remember, these three equations represent x-coordinate, y-coordinate, and z-coordinate. So it doesn't matter how it's presented to you. You should be able to make that connection. Okay. Any questions so far? Okay, one more example for you to try, a little bit more interesting. Find a set of parametric equations through the points negative 2, 1, 0, and 1, 3, 5, and where the line intersects the xz plane. Give you a couple minutes to think about it and start it, and then I'll go through it. if you're stuck. Hint, first you need to find a vector that represents the line, or that's parallel or on the line. Once you have that, you have a couple of options for the parametric equations. All right, how do I find the vector?
Subtract.
So yeah, you literally connect and make a vector out of the points on the line, okay? So if we go back to our diagram, you would be basically connecting the 2 points that are given to you, and there's your v vector. Does that make sense? Okay. And so if I do that, it doesn't matter which way you go, but I'm going to go 1 minus negative 2 is 3, 3 minus 1 is 2, and then 5 minus 0 is 5. So that's my vector v. And then from there, pick either point. I like that there's a 0 there, so I'm going to go with this one. My equations will be 3 minus 2t. Hold on a sec. Wrote that backwards. Negative 2 plus 3t. 1 plus 2t. And then 0 plus 5t.
Do you set the y equal to 0?
So you're talking about the next piece, right? So how do we find where it intersects the plane? You're absolutely right. On the xz plane, we know that y has to equal 0. Has to, right? So with that knowledge at hand, we can set y equal to 0 exactly as you suggested. Solve for t. And now that gives us when, a lot of times t represents a time parameter, so I like to say this gives us when it intersects the xz plane. Now to figure out the exact location, you should be able to plug in the t equals negative 1/2 in there. So we get x equals negative 2 plus 3 times negative 1/2. And you can simplify that. This will be negative 1, so negative 3.5. This is 0, and that's negative 5 over 2, or negative 2.5. And so those are your coordinates. This is the intersection.
Is it negative 2.5?
Yeah, I don't know why. Thank you. Make sense? Any questions on that? Okay. Again, prospect not here. Don't be afraid to just turn on your mic and yell at me, because just like you're in class, okay? All right. Next problem. Let's say I give you two lines, L1 and L2, and here are their equations. X equals 1 plus 4t, y equals 5 minus 4t, and z equals negative 1 plus 5t. Second line is 2 plus 8t. For x, for y, we have 4 minus 3t, and the z portion is 5 plus t. Okay, so first question. Are these parallel? If not, find the intersection if possible. All right, so now that we've reviewed how we know if vectors are parallel, why is this? Can you guys remind me? How do I know if two vectors are parallel?
They're scalar multiple.
Scalar multiples of each other. So let's extend that to lines. What do I know by looking at these about the vectors that represent them? Like, could I maybe write, let's say, V1? If V1 is a vector that's on L1, what vector must be on it? And we're just working backwards now.
4, -4, 5.
Good. And the line that would be, or the vector that's on the second line would be 8, -3, and 1. Okay. These direction vectors, I mean, it's promising when you see the 4 and the 8, right? But as soon as you get here, you realize these are not scalar multiples of each other. Okay? So V1 and V2, not scalar multiples of each other. So not parallel. So we've established that they're not parallel to each other. Now, to find the intersection, okay, so I just want to make a couple things clear. So let's say we have L1 looks something like this, and L2 looks something like that. Let's suppose there's an intersection point. So if they intersect, I just want to point out that these t values do not have to match. Okay? For instance, if t equals 1, maybe I get to this intersection point on the first line, but it might happen at a different juncture, maybe t equals 3, that it hits that same location. Does that make sense? We're not asking for t to be the same, we're just asking, do these lines cross paths? And it could happen at different times. It's almost like if two of us were walking, at different times, we're looking at our paths, right? Did our paths intersect? Does that make sense? Not necessarily are we both there at the same time. So with that being said, okay, what we need to do first is let T1 and T2 exist so that now we have x equal to 1 plus 4T1 and then x equals 2 plus 8T2. And I'll do the same with the other ones. Y is going to equal 4, whoops, wrong line. Y equals 5 minus 4T1, and y equals 4 minus 3T2, and z equals negative 1 plus 5T1, and 5 plus T2. Okay? So here's our new L1 and our new L2. To get started, okay, if these two paths intersect, right, then it's clear that the two x values have to be the same at some point, at some t value, right? Same with the y's, same with the z's. So first, we can start by saying, let's let 1 plus 4T1 equal 2 plus 8T2. Which doesn't quite help us yet, because now we have two variables, right? But looking at the next parametric set, we can write 5 minus 4T1 is going to equal 4 minus 3t2. And now this is looking better. This is just a system of equations, right? Two unknowns, two equations. I'm looking at this and thinking this isn't so bad. I can just add these right away and I get the t1s to eliminate, right? So if I add the equations together, we get 6 equals 6 plus 5t2. So that implies that t2 has to be 0. Okay, if t2 is 0, let's go back up here. 1 plus 4t1 would have to equal 2 plus 8 times 0, so just 2 basically. Okay, and so 4t1 is going to equal 1, and I'm getting t1 is equal to 1/4. Does that make sense so far? Okay, so I just want to illustrate, we haven't proved anything yet. We've just figured out when the x and y paths cross, right? It's possible that maybe we have skew lines, like so, right? Maybe they cross paths, but we have varying heights. So it's crucial now, once we know what t1 and t2 are, you want to check all 3 coordinates. Well, really it's just the last one. Okay, so if I take t1 and t2, I know that the x and y's are going to match. Everybody agree with that? Because, I mean, that's the way I set it up. Unless I screwed up, I know these two will match. The issue is going to be over here. So if I plug in z equals -1 plus 5 times a quarter, and then z equals 5 plus nothing, you guys see the z coordinates don't match, right? Okay. Z's are not the same. So these are skew lines. Any questions on that?
So they never cross?
Nope. So they're going to look, I mean, I can't. Here's a good example. Think. So if you think of a box, right, the edges, if you extend the lines, those are examples of skew lines, right? What we've just established is that the x and y coordinates match, but the heights z don't. So they don't intersect.
Did you say z equals 5?
For the second one, yes, because t2 was 4. Or I'm sorry, t2 was 0.
Oh, okay.
Right? So I'm plugging in t1 and plugging in t2. Does that make sense? And that's how I know that they don't match. Okay. Any questions? Okay. Almost done. To save time, when I talk about line segments, all I'm going to say is just restrict the domain. So for example, yeah. So if we use the same coordinates from the second example, if we have the points -2, 1, 0, and 1, 3, 5, and we just want the segment, not the whole thing, not the whole line, between these 2 points. We already know the equations because we did the work, so I'm just going to copy the answers down. It was x equals -2 plus 3t, y equals 1 plus 2t, and z equals 5t. So we've already figured out the equations, but now if we want to specifically talk about from this point to this point, it's very easy to do that. You basically just figure out what t has to be. Okay? So, I mean, you can do this by inspection. If you look at the first point, what does t have to be that produces this ordered triple? So first, we know t has to be 0, correct. Everybody good with that, right? The second point, maybe not quite as easy, but we can do the same thing. Just take one of them. Let's take 1. We know 1 has to equal -2 plus 3t. Oh, that's actually pretty straightforward. And here we get t equals 1. And you can kind of verify, if you plug 1 in, do I actually get the second point? And you will. Okay? And so now we've just figured out between 0 and 1 is the line segment, right? So we would just say, here is the parametric equations with the restriction that 0 is less than or equal to t, which is less than or equal to 1. So line segments are no different. You just have to add in from what t value to what t value produces that line segment.
Wait, so you use the x equation?
Yeah.
Either.
It won't matter, because let's say I looked at the z's to figure out the second value, right? 5 would have to equal 5t, so either way you're going to get t equals 1. Does that make sense?
Yeah.
And if you didn't eyeball it and say, oh, that's clearly 0 for the first point, again, set it equal, right? -2 equals -2 plus 3t, you get t equals 0. Same thing here, same thing there. Mm-hmm. All right. Finally, we have vector equations. And those look like this. If we're talking about lines in vector format, you can take each parametric equation and make it a component. So it'd be like x equals x naught plus at, y equals y naught plus bt, and then z equals z naught plus ct. Okay, or if you prefer, you can factor out this scalar, this parameter t, and so now what you can do is write it as x naught, y naught, z naught, and then add in the second vector, which is just going to be the scalar plus, or scalar times a, b, c. So if we kind of split this up into 2 vectors, this is probably the most commonly used vector equation because it looks just like the parametric form, right? If you focus solely on x, you guys see that, right? X equals x naught plus at, y equals y naught plus bt, and so on. It's the same thing, just written in vector format, okay? Now, we can go one step further. If we call xyz equal a radius vector r, and x naught, y naught, z naught, sorry, thank you, equal an initial radius vector r naught, and we still have v as our ABC vector. Now we can write it as radius equals initial radius vector plus the direction vector times t. This direction vector is just going to come from the coordinates of the points on the line. Okay? And it's not a huge deal in this unit, but I wanted to throw this out there now because it is totally related to parametric equations. Next unit, we will be doing a whole lot with vector-valued functions, and this is one particular example of that. Okay? Yes?
What is this equation again?
So this is just, again, the vector equations of a line. It's a different way. So basically, we've talked about two ways to represent lines today, right? Three ways: parametrically, symmetrically, and now we have a vector way of doing it. And it's really all related to, where's my first sheet? It all comes from this, right? They're all just variations of the very beginning, which is just the three parametric equations.